So in example number 4, we are going to translate from explicit rules to recursive rules. So if I'm looking at the first sequence, I have a sub n equals negative 6 plus 8n. I notice that this is an arithmetic sequence. So therefore I need to write the recursive rule. To write the recursive rule, I will need the first term. So I substitute 1 for n, so negative 6 plus 8 times 1. So the first term is going to be negative 6 plus 8. The first term is going to be 2. So now I need to write the recursive rule. So I know that the first term is 2 and the common difference is going to be 8. That's our rate of change. So for the recursive rule, I say the first term is 2 and a sub n will equal to a sub n minus 1, or the previous term, and add 8. So here is our recursive rule. For the second pattern, I can see that that's a geometric sequence. So this is geometric. So I need to find the first term. So the first term is going to be negative 3. So 1/2 to the 1 minus 1 is 1/2 to the 0, which gives me 1. Therefore, the first term is negative 1. The common ratio is 1/2. So I can write the geometric sequences recursive rule. So the first term is going to be negative 3, and the recursive rule a sub n is going to be the common ratio, or 1/2 times the previous term, which is a sub n minus 1. So the rule that I was given originally is our explicit rule. So this was the explicit rule, and this was also an explicit rule. And then we wrote the recursive rule for each one of them. In this case, we are given the recursive rule. So let me write that right above it. This is our recursive rule. And this is an arithmetic sequence since it has a common difference. So it's arithmetic sequence. So the common difference is going to be negative 2. And I also know that the first term is negative 5. So the explicit rule for an arithmetic sequence is a sub n equals the first term plus n minus 1 times the common difference. Since I know the first term, I can substitute that for a sub 1, which is negative 5. And I also know the common difference, which is negative 2. So now by simplifying, first distributing the negative 2 and getting a sub n equals negative 5 minus 2n plus 2. And finally, a sub n is going to be negative 2n minus 3. So here is now our explicit rule. So now we'll go to the second one, which is again a recursive rule, and it's a geometric sequence. And I know this because there is a multiplier of 2. So I know the first term is 10, and the common ratio is that multiplier of 2. So to write the explicit rule for a geometric sequence is a sub n equals a1 times the common ratio to the n minus 1 exponent. So let's go ahead and write the equation. So a sub n equals, the first term is 10, the common ratio is 2 to the n minus 1 exponent. So it is a little bit easier to write from the recursive rule the explicit rule for a geometric sequence. So next you will have a few monitoring progress problems, so please work them out before you move on to the next slide. So this is our first real life problem. It says a lake initially contains 5,200 fish. Each year the population declines 30% due to fishing and other causes, so that the lake is restocked with 400 fish. Write a recursive rule for the number of A of n of fish at the start of the nth year. Part B, find the number of fish at the start of the 5th year. And part C, describe what happens to the population of fish over time. So to write the recursive rule, we are going to start with writing the first term. So the first term in this particular sequence is 5,200 fish. And since it declines, the population declines by 30%, that means the remaining fish in the pond is going to be 70%. So it's going to be a sub n equals 0.7, the decimal form of 70%, a sub n minus 1, and then plus we are going to add 400 fish each year. To find the fish population after the 5th year, we are going to use our graphing calculator. So the first thing what I'd like you to punch in your graphing calculator is 5,200 and then enter. Then you're going to punch in 0.7 and then the times. Then you enter second and the minus symbol, which stands for the answer, and then plus and then the number 400. Then if you press the enter button once, you'll have the number of fish after the 1st year, and then press it again to find it after the 2nd year, press it again to find after the 3rd year, press it again to find after the 4th year, and if you press the enter 4 times, you should have the number of fish at the beginning of the 5th year, which is 2,262 fish approximately, and this is 2,262 because we don't have a 0.7 fish, so we have to round it to the nearest whole number. So if you press the enter 4 times, so 4 times, then you should have the answer for the beginning of the 5th year. Now keep pressing the enter button to find out what happens with the population of the fish over time. And what we notice if we press the button many times, that the fish population approaches to 1,333 fish. So after pressing the button several times or many times, you will realize that the number doesn't change significantly and it approaches to 1,333 fish. So now you have a monitoring progress problem where you have to follow the same process that you have done in this problem and answer the question. So please do that before you move on to the next slide. In this problem, again, this is a real life problem. It says you borrow $150,000 at a 6% annual interest compounded monthly for 30 years. The monthly payment is $899.33. Find the balance after the third payment. Due to rounding in the calculations, the last payment is often different from the original payment. Find the amount of the last payment. Again, in this problem, we are going to use our graphing calculator. So let us go ahead and start with figuring out the monthly interest rate. So since the annual interest rate is 6%, that written as a decimal is 0.06. And so for monthly rate, we are going to do 0.06 divided by 12. So we are going to get an answer of 0.005. So now we can start out by saying our first term is going to be 150,000, and to derive the nth term, we are going to have to multiply the previous term by 1.005, and that's because the interest is adding to the amount, so that's why it's 1.005. And then we are going to have to subtract the payment, which is $899.33. So here is our equation. And again, we are going to start on the graphing calculator by first typing in 150,000 and enter. After we press the enter button, then we are going to say 1.005, then times, which is the multiplication button, and then second, and the negative symbol, which stands for the answer, and then subtract, and then press the number 899.33. Then press enter 3 times. To figure out how much the balance will be after 3 payments. So the balance after 3 payments will be $149,549.77. Now we need to figure out how much the last payment would be. So we are going to enter as many times as necessary to get near $899. So we are going to press the enter button all the way until you see your calculator showing a couple of $1,000, then slow down so you can figure out what the last payment amount will be, which will be a little bit more or a little bit less than $899.33. So if you go 360 times, then you are going to get the last payment. So the last payment is going to be $895.42. The next problem is going to be a monitoring progress problem that you have to follow the similar process that you have done on this problem. So please move on to the next slide only when you finished the monitoring progress problem. See you guys at the next lesson.